Now we arrive at one of my favorite topics, NMR spectroscopy. By the end of today's lecture, you should be able to use NMR spectroscopy to determine the number of non-equivalent hydrogen atoms or carbon atoms. Use NMR spectroscopy to deduce molecule structures. Now this, of course, will be also done in concert with data that we can obtain from IR spectra as well. There are two different kinds of NMR we discuss in undergraduate organic chemistry. Hydrogen NMR, or H1 NMR, also sometimes called Proton NMR, and C13 NMR, or Carbon NMR. I'll begin, of course, by teaching you about hydrogen NMR. Typical hydrogen NMR spectrum looks like this. These peaks are each produced by a different kind of proton. By learning where different kinds of protons show up on an NMR spectrum and what they look like, we can deduce compounds' structures. So you may ask, Mike, what do you mean by different kinds of protons? Well, if two separate protons are in exactly the same environment, that is, they have the exact same stuff all around them in all directions, then they are the same kind of, or equivalent, protons. You should already understand this, of course, but to put your knowledge to the test, I ask you, how many different kinds of protons are there in each of the following molecules? The answer to each of those questions tells you how many different signals you'll see in the proton NMR for those molecules. Now in proton NMR, you'll also see that each peak has a little sigmoidal curve above it. These sigmoidal curves are called integrals. Their heights tell you the proportional number of hydrogens that each peak represents. For example, let's say that I've measured the heights of the two integrals shown here, and I found their relative heights in proportion to each other to be 1 to 3. What does this mean? Well, it means that the signal to the left could be a CH and the signal to the right could be a CH3. But remember that these heights are proportional. In other words, I could multiply them both by 2 and get a 2 to 6 ratio. That would probably correspond to a CH2 and 2 CH3s. Or I could multiply them all by 3 and get a 3 to 9 ratio. In that scenario, this would probably represent a CH3, and the one on the right would represent 3 separate but equivalent CH3s. Got it? Now, this process of measuring the heights of the sigmoidal curves that are used to deduce structure is called integration. The sigmoidal curves themselves are also called integrals, not to be confused with integrals from your calculus classes. So are you ready to see a compound that produces this HNMR? Here it is. So you'll notice that this CH3 right here corresponds to this peak right here in pink. And these 9 hydrogens here are all equivalent. So they give one peak right here that corresponds to 9 relative to this peak's height. So at this point you should be wondering, where do different hydrogen peaks actually show up? The answer to that depends on their individual partial charges. Generally speaking, the more positively charged an individual hydrogen is, the further to the left it will appear on an HNMR spectrum. The more negatively charged, the further to the right it will appear. We say then that further to the left equals more downfield equals more de-shielded, or in other words is the same thing as saying more positively charged. And in contrast, further to the right on an NMR spectrum equals more upfield, more shielded, and hence more negatively charged. Remember that the electron cloud around a hydrogen atom is kind of like a shield. The more de-shielded the hydrogens become, the further to the left they appear on a proton NMR spectrum. These are some of the pictures of different things from movies that had electronic shields around them. If, for example, the Death Star right here were a hydrogen, then the more you removed its shield, the more positively charged it would become, and hence the further to the left or further downfield it would appear on a hydrogen NMR. Now you can see Admiral Akbar smiling here in the background. So I ask you, For each of the pairs of molecules shown here, which hydrogens do you think are more positively charged and hence will appear further to the left on a proton NMR? And why do you think that? Now, if you want to, you can pause the video here and consider the answers before going on. Most organic textbooks give lists of where different kinds of hydrogens show up on proton NMR. I personally think those lists are usually way longer and more complicated than I would personally prefer. Here's my list. Hydrogens that are stuck to sp3 hybridized carbon atoms, single bonded CH3s, CH2s, and CHs generally show up about 1 to 5 ppm, which are the units we see in proton NMR, depending on what other atoms are stuck to or near the carbon atoms. There are exceptions to this, but I'm trying to teach you the general rules. Of course, as we showed in the previous slide, hydrogens that are stuck to sp3 hybridized carbons that are near more electron withdrawing groups will be further to the left and hence closer to 5 than analogous hydrogens that are not, which will be further downfield or closer to 1. Hydrogens that are stuck to sp2 hybridized carbons, that is double bonded CHs, appear from 4 to 6 ppm. Hydrogens that are stuck to aromatic carbon atoms, benzene ring hydrogens or other aromatic carbons, appear generally speaking about 6 to 8 ppm. Aldehyde hydrogens, generally speaking, appear right around 10. Phenol hydrogens sometimes appear at the same place, although I've seen them appear in other places, and they can vary depending upon the solvent and concentration in which the proton NMR is run. Carboxylic acid hydrogens usually appear 12 to 14 ppm. Amide hydrogens sometimes appear 11 to 13 ppm, although once again I've seen a lot of variability there. Alcohol OHs appear 0.5 to 5.5 ppm, and amine NHs appear 0.5 to 5.5 ppm as well. Once again, in these last two, I've also seen a tremendous amount of variability depending on the concentration or the temperature or way in which the sample is run. Now let's see if I can describe that same thing in picture form. Once again, as I mentioned before, hydrogens that are stuck to sp3 hybridized carbons, generally speaking, will appear between 1 and 5 ppm. I personally like to call this single bond land, because we're talking about carbons that have all single bonds around them. The hydrogens stuck to those carbons appear, generally speaking, in this area. 4 to 6 is what I call double bond land, hydrogens that are stuck to carbons that are double bonded to other carbons. 6 to 8 are hydrogens that are stuck to benzene, or it could be other aromatic compounds. I call this aromatic land. Right around 10 we see phenols, that's this type of hydrogen, or aldehydes, this type of hydrogen shown in pink. 12 to 14 we see carboxylic acids and sometimes amides, although sometimes there's some variability here. And alcohol hydrogens and amine hydrogens generally show up in this range, 0.5 to 5.5 ppm, although there is sometimes a lot of variability there.